So today we're going to review a question where we do mesh analysis. As you notice here in this circuit, there's three meshes. We have our I1 mesh, our I2 mesh, and we have a third I3 mesh. So the next thing that we notice is right between our I1 and our I2 mesh, we have our 0.5 amp current source, which results in the formation of a super mesh. And that specific reason, as proven in one of my previous videos, is because when we're doing mesh analysis, we're trying to represent voltage drops in terms of Ohm's law, and we can't apply Ohm's law to represent the voltage drop across that independent 0.5 amp current source. So then starting with this, we come up with our first KVL super mesh equation for mesh analysis. So we apply KVL at our super node. The way I do this is I would say that all my resistors are passive, and I would just assume there is a voltage drop across every resistor, and then the voltage sources, I would follow the polarity that's given. So then we go around this super mesh, we end up with 5 times the current in I1, 20 times the shared current between I1 and I3 in that branch, plus 10 times the shared current between I2 and I3 in that branch. Since my net direction is clockwise for my super mesh, I have to make sure that when I'm doing I2 minus I3, I'm taking the one in the direction of my KVL loop minus the one moving in the opposite direction for my shared branches. So with that, we have our first equation. Now for our second relationship, instead of applying KVL at our I3 mesh, because we have that dependent current source in the branch within the mesh, we can come up with a simpler relationship. So looking at the way Ix is noted in our diagram, we notice that this current is also represented by our I1 mesh current that we've notated. So an important thing is just to make sure that we're watching the directions. So in this case, we notice that I1 and our Ix define directions. If we were to trace it, they are going in the same direction. So we can account that Ix is a positive I1 value. And then our third relationship that we can come up with is through that super mesh 0.5 amp current source that we see. And from that, we know I1, because it's going in the same direction as our independent current source, minus I2, that's going in the opposite direction of this 0.5 amp current source, will get us the value of the current in that branch. And so just before we move on, we see from our dependent current source that we have I3 has to equal 4I1 because I1 is Ix. So from here now, we have, as we can see, 3 critical equations outlined at steps 1, 3, and 4. So from equations 1, 3, and 4, we have a system of 3 equations that have 3 unknowns in terms of our I1, I2, I3 mesh currents. And so essentially at this point, it's solving the system of equations for the 3 unknowns that we have. And once we've solved it, we should see that we get I1 is negative 0.291 amps, as we can see. I2 should be negative 0.79167 amps, or 792 amps. And I3 should be negative 0.991 negative 1.167 amps would be I3, is what we find. And so the negative specifically in this case, their significance is that it implies, as you can see, we've defined our mesh currents to go in the clockwise direction. So what this implies is that in actuality in the circuit, our mesh currents are flowing in the counterclockwise direction. So in this case, just because of the way that we've defined our mesh currents, we end up getting a negative answer, which just implies that our mesh currents are going in the counterclockwise direction. So I'm just going to notate that down here so that we know that all currents are in the counterclockwise direction, as that often it may be a part of the answer to describe the direction that the currents are actually flowing in.